Hello again, my dear students. Now this is the final lecture, the final chapter in our solid state electronics course for academic year 2020. It's a long journey together. It's a 12-week journey when we start together in week one in, I believe, in September 2020, September 2020 or October 2020, when we start together. I believe it was October 2020 when we started together this journey with the solid state electronics course, and now we reached the final stop, the final point in our module. Usually, the final lecture in any of my modules, I try to make it in somehow a different manner. It is something more toward technology. It's something more toward most recent technology. And in this module, I choose the tunneling field effect transistor, or the TFET, as a topic for the final lecture. As I mentioned, it's something different. It's more toward a concepts lecture. It's more toward a knowledge lecture. So we will not find a tutorial problem set related to the module to this lecture. Maybe the lecture script will be somehow different, which tackle more a realistic data from the rail industry about the fabrication of the tunneling field effect transistor. So by something or another, it's a lecture with a different flavor, I can say. So now please permit me to start sharing my presentation. It will be a very short lecture with respect to other lectures which somehow exceeds 2 hours in some cases. Now it will be something like 20 to 25 minutes lecture just to describe the concepts of the tunneling field effect transistor. So let's start the journey together. Okay, so let's now start showing the presentation. I hope you can now see my presentation well, and also let's start operating our laser pointer. Here, so this is what's called the tunneling field effect transistor, or the TFET. By the way, in literature, whenever you are searching for the TFET, you will find two types of TFET. You will find what's called the thin film field effect transistor, and also the tunneling field effect transistor, and actually both of them are with a wide range of application in the current industry. For example, for the thin film field effect transistor, or the or the TFET transistor, these transistors are widely used in the organic LEDs televisions nowadays, the OLED LEDs, which is already on market nowadays. And of course, it has a very, very important commercial or market share in the electronics market nowadays. Similarly, when we are talking about the tunneling field effect transistor, the tunneling field effect transistor is somehow a bit old with respect to the thin film effect transistor, but it's still one of the very important and very interesting transistors. Maybe also as a future topics, you can read about organic electronics, or the organic FETs, or what's called the OFET. The organic field effect transistors are those transistors where the semiconductor is implemented using an organic material. Maybe this is somehow an advanced topic that you may be interested in having a look on it during your next semesters or next projects, inshallah. So let's now start our journey with the tunneling field effect transistor, or the TFET. And let's start with the motivation. Why we are interested in finding new architecture to the FETs. We already have studied the metal oxide semiconductor field effect transistors, or what's called the MOSFETs. And I believe you know already that the MOSFET is the most famous electronic device nowadays in all electronic industry. But the question will be,
why we are searching for other fits, why we are searching for another types of field effect transistors, why we are searching to upgrade the MOSFETs. The question is very simple. Whenever you have a new technology in the processing technology, for example, in the Intel processor in your computers, or for example, in the embedded systems, in the ARM processors in your PlayStations. So whenever we have a new technology from the consumer point of view is reflected with a higher speed processor. You need to have a processor who performs the same tasks in less amount of time. So that's why we have the i7, i3, and i5, and all, and the Xenon processor, and all these types of processors. In the past, we were dealing with the Coach2 processors. Maybe you don't hear about it, or you hear before. So these are all new generations of processors, and the main target is to increase the time. So how we are going to increase the time? Simply, we are going to increase the time by adding more computational facilities in the processor. If the processor is capable to perform the computational facilities in a better manner, then it will do it faster. So simply, we need to increase the number of transistors per processor. Or in other words, we need to reduce the dimension of a process of a transistor. So if you remember the first lecture, when we were talking about what's called Moore's law, where maybe 40 years ago or 50 years ago, when Moore starts to say, please expect that per each 18 months, the number of processors, or sorry, the number of transistors per unit area will be doubled. So this is simply how processors are upgraded. Whenever you increase the number of transistors, you perform the tasks faster. And in order to increase the number of transistors, you have to reduce its area, its dimension. Herein, we reach what's called the bottleneck, or the saturation point for the MOSFET industry. Whenever we are going narrower, narrower, and narrower. By the way, in the MOSFET industry, we classify the technology based on the channel length. So when I told you, for example, in the past, we were using a 60 micrometer technology. So this 60 micrometer technology is simply the channel length. This was something like 10, 15 years ago. Now we are using up to 7 nanometer technology. So what I mean by 7 nanometer technology is the channel length of our MOSFET is 7 nanometer. But frankly speaking, we are not able to reduce the channel length of the MOSFET using its classical structure. What I mean by classical structure is the structure we deal with in our course, this source, drain, gate oxide, and gate structure. So using such a structure, we are not capable to reduce the overall dimension of our MOSFET. Okay, so using this ordinary structure for a MOSFET, we are not capable to reduce the dimension of the MOSFET. We have a bottom limit. We have a lower limit for the dimension. Herein, we have to search for different architectures, different concepts in order to implement the same idea. And this is where another architecture starts to appear. Herein, we have a huge amount of modifications. So you can Google, for example, what's called the multi-gate field effect transistor. So from the name, you can understand that this is a transistor with different, more than one gate. or what we can call the bottom gate structure or architecture. So in this structure, the gate is turned to be in the bottom rather to be in the top. Also, we have different architectures. One of the most famous architectures, by the way, is the flipped gate architecture, and this architecture is used by Intel in its processors. So we have different architectures. The main advantage of these architectures is its capability to reduce the dimension of the MOSFET, where the ordinary or the conventional structure cannot be able to be implemented. So one of these technologies is the tunneling field effect technology. So as you can see here we are talking about the industry. The first point toward the industry is changing the material. So as I mentioned different time in my course, that silicon is the most famous semiconductor material. But sometimes we have to change another material. So here, for example, by the way, this presentation is captured from Intel. So this is data related to Intel. So here, for the MOSFETs, for example, this is, for example, in indium arsenide semiconductor, where we implement our TFET. So it's a new material, it's a new technology, and we are combining them, or we are comparing the silicon one with the indium one. Here, the comparison is implemented in terms of in terms of the current and in terms of the voltage. It's ID versus VGS, and this, as you can see here, is the different performance of both the tunneling field effect transistor and the normal MOSFET. Here is what about delay. So please remember, we are seeking for a minimum time. So delay is a very important parameter. And here you can see how the tunneling field effect transistors increase or boost the processing capabilities of the MOSFETs of the FETs. Here you can see that the targeted tunneling field effect transistor is 8 times faster than the normal MOSFETs. So that's why we are seeking for a new technology. So let's now go into the details. What are the tunneling field effect transistors? So here we start to introduce a very important types of junctions. If you flash back our course, you will find that we have dealt with different types of junctions. We start with the PN junction, if you remember. And then from the PN junction, we go to the MOSFET, where we introduce new types of junction, like we have a metal semiconductor junction or a metal oxide semiconductor junction, the MOS junction or the MOS junction. And also in the BGT, in the previous lecture, we introduced the PNP and NPN junctions. Herein we have a new type of junction, and this is one of the important junctions in semiconductor electronics, which is the PIN junction. What do we mean by a PIN junction is simply that we have a p-doped material, an intrinsic material, and then we have an n-doped material. As you can see here is a source and a drain. So if we make some sort of analogy or a comparison between the ordinary MOSFETs and the tunneling field effect transistors, we will find as follows. We will find that now the first change is that the source and drain are not similar. In the ordinary MOSFETs, we have the same type of doping for the source and the drain. So it's either an N-channel MOSFET or a P-channel MOSFET. But herein, in the tunneling field effect transistor, we have a source of P and a drain of N, or the vice versa. So this is the first change. The second is in the MOSFET we have either a P substrate or an N substrate. However, here the substrate is intrinsic, or on the other word, the channel is intrinsic. As you can see, here we still have the gate oxide and the gate cut. So let's first start to plot an energy band diagram for the PIN junction. Here, please let me use my whiteboard in order to plot the energy band diagram for a PIN junction. As usual, I believe we do it more than once. So as usual, whenever you start to plot an energy band diagram, you first start to plot each region individually. So you say that, okay, I have a PIN junction. A P junctions, that means that we have, or a P regions, that means that we have a Fermi level which is more close to the valency band rather than to the conduction band. In the intrinsic region, we have the Fermi level directly in the center. The Fermi level is overlapped over the EFI or the Fermi level at intrinsic. And in the N region, we have a Fermi level which is more close to the conduction band. So this is the first step. The second step is we start to merge all these junctions or these regions together, and our reference under thermodynamic equilibrium is the Fermi level. So the Fermi level should be constant. This is the Fermi level that should be constant, and then we start to plot everything with respect to this Fermi level. So here is a p-type region. And then this is the N-type region, sorry, the intrinsic region, and finally this is the N-type region. So this is the overall schematic for an energy band diagram for a PIN junction as follows. So what if we increase the doping? So increasing the doping means that if you increase the doping for the p-type material, this means that simply this region or this distance starts to decrease. If you increase the doping for the N-type material, then that's simply that this region starts to decrease again. So in the Fermi level, in the N region, the Fermi level more toward the conduction band, and in the P region, the Fermi level is more toward the valency band. So what if we do so? What if we do so? We will return back. Let me return back to my presentation slides. So if we do so, we will find an energy band diagram that looks like that. And what is interesting here is the valency band of the p-type region becomes aligned with the conduction band of the p-type of the n-type region. So if you can see my plot, this one and this one becomes aligned. How they are become aligned? Because simply you are giving this upward and you are pulling this downward. So this region and this region becomes aligned. Whenever these regions becomes aligned, then if you have a great potential, if you have a very large amount of energy, electrons here in the valency band of the p-type can tunnel the channel, which is this blue area, and jumps to the green area here, which is the conduction band of the n-type region. So electrons now are tunneling the channel, or sorry, are tunneling the energy band gap. This is a forbidden gap, but whenever we have a very great energy, you can tunnel it and pass to the other region. This is simply the concept of the tunneling field effect transistor. By the way, we are not capable to study the mathematical model of this tunneling field effect transistor because simply this model is based on a quantum theory where we did not have the sufficient background to study. Herein, we just describe the concept of how tunneling field effect transistor works, how electrons tunnel the band gap and go from the p-type region, which is the source, to the n-type region, which is the drain. So current flow in this direction, as you can see, or sorry, electrons flow in this direction, as you can see, and then you have a current. This is simply the concept for the tunneling field effect transistor. So we can implement such a tunneling. Again, here this is some equations based on the quantum tunneling. Of course, this is just for your information. You are not requested to know anything about that. This is just for your information. So this is the concept. This is a very simple concept. We have this is the MOSFET. This is the ordinary MOSFET, where, as you mentioned, you have the source and the drain, both of the same type of doping, and you have a substrate with a different type. Herein we have a source which is a P, a drain which is an N, and what is in between is intrinsic. This is an energy band diagram for the cross-sectional area for that NPN junction in the MOSFET. I believe we already spent a lot of time in understanding this, and here is the energy band diagram for the tunneling field effect transistor. As you can see, my dear students, the Fermi level is now inside the valency band and inside the conduction band. And if you remember, we already studied this case and we called the degenerate semiconductor material. So as you can see here, you should implement your p-type and n-type regions, which is the source and drain, to be a degenerate semiconductor material in order to perform this tunneling impact across the energy band gap. So this is simply the concept for the tunneling field effect transistor. Here, we also have to introduce a new concept. This is, I believe, your first time to deal with it, which is called the homojunction and the heterojunction. So to make it simple, whenever we have, for example, a diode is a p-n junction. So whenever we have a diode, then we say that we have a p region and n region, and we assume that both are the same material. So you have a p region of a silicon and you have an n region of a silicon, and you combine both together. But actually, this is just an assumption, or this is just a case. Principally, you can create a p-n junction with two different materials. So for example, you can pick up a silicon with a p-type, with a b doped, and gallium arsenide with an n doped, and combine them together. Herein, we will call it a heterojunction. So a homojunction means that you are creating a junction of two different doping, but the same material. But a heterojunction means that you are creating a junction of two different doping and two different materials. So in this PIN structure, you can use either the same material in creating the P, the I, and the N, or you can use three different materials, as you can see here, in creating this PIN junction. That's why we call this a heterojunction PIN junction, or a hetero-PIN junction. So this is simply the difference between the homojunction and the heterojunction. Herein is our structure. This is what's called a scanning electron microscope for these structures. This is a silicon TFET, I mean a TFET implemented using silicon, and this is the corresponding IV curves for this structure. Of course, this is for your knowledge. And here is also another structures or another materials that can be used in order to implement the TFET. Again, these data have been captured totally from the Intel website. So this is different Intel processors using, or different Intel transistors using the TFET technology. This is another structure for the TFET. It's somehow a more complicated structure, as you can see, with different materials, with different compound semiconductors, in order to implement this tunneling field effect transistor. The same concept is applied, but with more sophisticated materials and devices. Again, this is just for your information. You are not requested to memorize or study this for your final exam. And again, here, this is another model, as I mentioned earlier. In order to study such a structure, you have, you have to have what's called atomistic quantum modeling or quantum modeling for your devices, because these devices are not able to be described by our drift diffusion model. If you remember, I believe my lecture number 4, the last lecture in the material part, in the last slide, I mentioned this word. Whenever we are going narrower than 1 micrometer, we have to kick out the classical or the semi-classical drift diffusion model, and we have to use a quantum modeling here in an atomistic quantum model for the tunneling field effect, again tunneling field effect transistor. Again, this is also for your knowledge. Here you can see that this is the the p-type source, this is the n-type drain, this is the energy band gap, and here electrons will start to move, as you can see here, from the the source. Here's S stands for the source which is the p-type, to the drain which is the n-type, and the electron starts to flow. And this is the corresponding IP curve. So as you can see, after applying a voltage, this is at 0 voltage, you have a huge channel or a huge gap. Whenever you apply the voltage, the gap is become narrower, so electrons will tunnel faster. Whenever you decreasing the tap, electrons will tunnel faster, and that's why we have a higher current here, as you can see, which is the comparison between a lower voltage, which is typically 0, and a higher voltage. So the voltage here actually control the distance between the source and the drain. So you can understand that now you control the width of this tunneling channel by controlling the voltage across the gate. So by increasing the gate voltage, the channel becomes narrower, so more electrons can tunnel from the source to the drain, while whenever the voltage is lower, the channel is wider and less electron can tunnel till you reach the 0 voltage where no electrons can tunnel theoretically. So this is why we are using the concept of the modeling in order to understand, and herein you can actually also understand the threshold effect and what's called the sub-threshold effect. Because as you can see here, whenever we are below threshold, theoretically in the MOSFET we say that whenever we are below threshold, no current will pump. But practically this is not true. In the MOSFET and even in the tunneling field effect transistor, we have what's called the sub-threshold effect. And the sub-threshold effect can be described here by monitoring the current and voltage variation below the threshold voltage. So this is a very important example. Again, another data related to the ID and VGS at different configuration and at different channel lenses and gate lenses. Again, this is for your information. More data here. And finally, we can say that, again, the board capacitance. If you remember, we use this in our PN junction. We say that we have an internal capacitance. In our MOSFET, we study the CV curves and we study the capacitance of the MOSFET. Of course, in the BGT, unfortunately, we didn't have enough time to go into the internal capacitance of the BGT, but frankly speaking, it has a capacitance because simply a BGT is considered as a 2 PN junction. And we know that for a PN junction, we have a capacitance. So obviously, a PGT have an internal capacitance. And here, of course, again, in the tunneling field effect transistor, we still have a capacitance between two conducting mediums, the P as a source and the drain, the PNN, and an unconducting medium, which is the channel. So we have still the capacitance effect. And of course, this capacitance effect is very important, very considerable. As I mentioned, it was a very short lecture dealing with these concepts of the tunneling field effect transistors. So now this is the end of our module. This is not only the end of these lectures, this is the end of our module. I hope that you have learned, enjoyed this module. It's your first electronics module. I believe that it's somehow a tough module because we deal with different perspective of electronics, the physical perspective, the semiconductor perspective, sometimes even the chemistry perspective, and also the circuits and the mathematical perspective. So that's why it's a tough course. However, I believe that maybe in your next courses, I mean, especially the coming courses, electronics 1 and electronics 2, life will be a bit easier whenever we will leave all these sophisticated concepts related to semiconductor physics, and we will go to the electronics and the circuits perspective. So starting from the next course, you are going to study all these devices again, but 100% from a circuit or from an electronic perspective. You will deal with the PN junctions, I mean the die, the MOSFET, the BGT as a circuit schematic, like a resistance, like a capacitor, like a coil, like a voltage source. And in this case, I believe that life will be a bit easier than we have learned in our semiconductor or solid state electronic course. So thank you very much for your understanding. Thank you very much for your participation, for your contribution among the previous 12 weeks. I hope that we did a good task. I hope that we satisfy your needs in understanding these basic foundational concepts related to semiconductor physics and solid state electronics. Thank you very much for your concentration and see you in your next courses, inshallah. Thank you and bye-bye.